next speaker. This is Professor Claire Tomlin. Professor Tomlin is a professor in the EECS department at UC Berkeley, and she works in hybrid systems and control with applications to air traffic systems, robotics, and biology. And Professor Tomlin was among the pioneers of applying the Hamilton-Jacobi-Isaacs PDE for reachability-based safety analysis. So I think it was really exciting to hear about recent work in Marco Pavone's talk, and I'm very much looking forward to hearing from Claire Tomlin's recent work. So Professor Tomlin, please welcome.
Thank you. Thanks, Nikolai, for the introduction, and thanks for organizing, to you and your students for organizing this this great workshop. Okay, so I'm going to talk about kind of four things in a sequence. The first is to introduce or kind of review reachability, and then I'm going to talk about navigation in unknown environments as being a challenge, and you know, what are the things we can't do with that. So it's sort of more of a topic of things that challenges that open problems that we don't know how to solve yet, with some of the issues there. And then I'll talk about how we've made maybe a first step in bringing reachability into the safety analysis of this navigation in the unknown environment problem, and conclude with kind of some of the directions that I think are interesting to, and some of the things that we're starting to work on. Okay, so I had a student in my group, Samuel Bansal, who's now graduated, and he's going to be joining USC this fall. He worked at Skydio for a summer, and we've maintained a really nice connection with Skydio and the researchers there. So it's basically like this amazing flying camera that can track you as you do all sorts of things like sporting events. And several of my students have worked at Neuro. This is a delivery vehicle. It's now doing pizza delivery around the Bay Area, I just realized. But a couple of students have worked there and are working there now, really looking at the problems of, in both of these, problems of, you know, the connection between perception, learning-based perception and action, and the that kind of perception, planning, and control stack, and how these different modules are related and interrelated with each other. And I think, you know, from the point of view that I'm going to start with, we've been, which is a reachability point of view, has been a nice framework to kind of bookkeep information we know about the system and how it relates to safety. But it doesn't yet really address the kinds of problems that I feel like we need to address in learning-based, in safe learning-based control, like those that come up in navigating in unknown environments. Okay, so I'll start by talking about reachability. So this goes back, you know, to work. You know, I think one of the kind of pioneers of thinking about reachable sets and control problems is Dimitri Bertsekas, who really formulated reachability from a discrete time point of view. Our work kind of in reachability, it started a long time ago with Shankar Sastry and John Ligaros and George Papas. And then over the past couple of decades, both then and also in my research group, we've been trying to formalize it, trying to do computations in high dimensions. But the idea has always kind of focused on, given a model of the system, and here that's represented as a differential equation with a state X and an input U and disturbance D. You have this model F, which is assumed to be known. What you don't know about the system are these disturbances, but you assume that you know some bound on the disturbance. So with that framework, suppose, and let's talk about from the point of view of safety. So suppose you had unsafe configurations, like, you know, a collision set might represent that red ellipse that I've shown there. So the backwards reachable set is, from this red ellipse, is all states for which, for all possible control actions, actions that you can do to avoid collision, there's a disturbance action which can drive the system state into that red region, which we'll call G at time 0 in T time units. And we call that set G of T, and it's pictured here in pink. Okay, so it doesn't mean that those states will evolve into G of 0, but it means that if you're inside that set, and even if you apply the best case control action to keep you out of the red set, a disturbance or just the dynamics of the system could force you into that unsafe region. And this control disturbance kind of relationship makes us think about a game between two players. So we, in fact, use, instead of an optimal control framework, we're typically using a game framework where the player, one player represents the control actions and the other represents the disturbance actions. And doing this, we characterized, and again, there's been a lot of work on this, and I'm just referencing a few that have made contributions over the years in this, that you can characterize, and I'm showing it here kind of stylistically, it's sort of an iterative dynamic programming argument, but you can characterize that backwards reachable set as the sub-zero level sets of a value function or a cost function, or what it is a Hamilton-Jacobi-Isaacs function, J of xt. And that function, J of xt, solves a particular Hamilton-Jacobi-Isaacs equation, that PDE, which is shown there. The min with 0 on the right-hand side is the unusual part, which, or kind of an unusual component, which enforces that if a state is unsafe at any time within that horizon, from 0 back to time t, some negative time at which you start, because it's a backwards reachable set, then that state has to stay unsafe. It's unfrozen at unsafe. It can't become safe at a future time. Okay, so this is computing this requires, in general, for dynamics that are nonlinear or hybrid dynamics, it requires gridding. It requires a numerical method that grids up the state space. And a lot of the work in our group and in other groups has focused on developing efficient computational methods to solve these for reasonable or high dimensional control problems. So one of my first PhD students, Ian Mitchell, worked on something called the level set toolbox, and the code is available at that first link there. And in our research group, really over, I would say, the past 6 or 7 years, we've been developing kind of a wrapper to apply around this level set toolbox. Mo Chen and Sylvia Herbert have been really instrumental in doing that. And that link is also provided there from our GitHub site. And you can download the code, you can change the dynamics to dynamics, some of these examples, you can change the dynamics to dynamics you're interested in, and then you can just run the code and compute backwards reachable sets for given value functions which represent capture regions. Either you want to stay outside a region or get inside a region. But it's a neat tool for control because you're representing sets implicitly by the sub-zero level sets of this function J of xt, and you get information from that function J of xt, whether it's inside the set for a state x or outside the set for a state x at time t. But then also, depending on how you represent that function, maybe it's a signed distance function that you initialize with, you can get information about the distance to the boundary and information that's useful for control. Okay, so this is an old example. It was, that's actually Robley Field at Stanford. So I was still an assistant professor at Stanford. And these are, and you can kind of tell by the vintage of the quad rotors, these were quad rotors that we actually built with carbon fiber tubing, and we designed the PCBs to go on board. So this was before you could buy quad rotors very easily. But it's a collision avoidance problem where each quad rotor is running a collision avoidance algorithm based on a backwards reachable set computation with each of the 3 other quad rotors. And so on the right-hand side is a snapshot of the data showing the quad rotors and the backwards reachable set at any instant. So the students under that little tent there are joysticking the quad rotors around. And when one quadrotor gets onto the boundary of the backwards reachable set with another quadrotor, the safe control, the automated system takes over and guides the vehicles away from each other using that max over u, using that control that comes out of the Hamilton-Jacobi-Isaacs formulation. And then at some point, control is given back to the students. That's not an ideal transfer, but it's just sort of to demonstrate that this procedure, it gives you a set, which is interesting. It also gives you a control action to apply on the boundary. Otherwise, the students are just flying them in any way they want to. We actually tried to tell the students to get them to collide with each other. Okay, so that's sort of starting out, and we've done quite a bit of work. We and actually a whole community of people, of which I've seen a few people during this workshop who work on these problems of reachable sets, model checking in high dimensions, and dealing with the curse of dimensionality. I'd like to just spend another minute talking about this method that we've been developing recently with Samuel Bansal. This is a problem which tries, or this is a computational method for computing reachable sets, or in general, computing solutions to the Hamilton-Jacobi PDE. So that gives us the reachable set and the control action. But we've been looking for a long time at grid-based methods and approximate grid-based methods for doing that, like the level set methods are that Ian originally developed. And this is a grid-free method. And it's interesting. We call it deep reach because we're using a deep neural network to approximate the solution to this Hamilton-Jacobi-Isaacs function. So the idea is it's a self-supervised approach where you randomly sample points xi, ti, so in state and time, and then you compute the loss function at those states and times. And the loss function, if you kind of take a look at it, it's got two terms there. The first term is the deviation from the PDE being it's the error in the PDE itself. So that first term in the loss is just, if that term is non-zero, it means that you're not satisfying the PDE. If that term is equal to 0, that's the definition of the PDE. And then the second term is the initial data that you have for your PDE. So that combination, that sum of those two components, we define as a loss. And then we compute that loss at a set of randomly sampled state and times, and then we fit the parameters based on that error, and then we repeat. So it's a self-supervised method in which we don't even have to give samples of what the value function looks like. I mean, that's the part that's hard to compute, right? We just need to give it, points in state and time, these random samples in state and time, and it will compute the loss function at those and update. So it's been, and there's quite a few other papers going on right now about the use of deep learning in solving high dimensional PDEs, whether they be Navier-Stokes or other interesting problems. But this turns out to work quite well for, at least we've done some reasonable dimension now problems, which I'll just talk about in a second. Like, for example, this is a 9-dimensional collision avoidance problem. There are 3 aircraft, they're 3 dimensions each. And typically, to solve this, we've never been able to solve this exactly before, but we've tried things like approximating this in our 4 aircraft example that I showed you earlier. Because they were quadrotors and they could hover, we could actually decompose that 4 aircraft problem into pairwise. So we were able to solve and come up with the union of the pairwise unsafe sets gave us the correct unsafe set for the group. But that only happens in special cases. It doesn't happen when you have these generalized aircraft. So we've computed this unsafe set for this game problem where we have a single pursuer and 2 evaders, and this pink set is a 2-dimensional projection of what is a 9-dimensional set into x7 and x8 represent the position coordinates for the pursuer. So, for example, if the pursuer starts at this purple dot, which is inside the unsafe region, it means that the pursuer has an action which, whatever those evaders do, will cause a loss of separation between any pair of aircraft. If that pursuer starts right outside the pink zone, regardless of its best case trying to cause any pair of aircraft to collide, you get a safe situation. So, you know, this is kind of exciting for us that we've now been able to kind of tune this using a deep network, which is based on activation functions, which are sinusoids, so that you can, so it's a sinusoidal representation network, so that you have a good representation of the gradients as well of that value function. Here's a 10-dimensional example that we've solved. We just presented this the other day. It's a paper, well, I've given you the archive link there, but this is a paper that we presented in this ICRA conference. So this is a two-car, 5 dimensions for each car, and each vehicle Q1 and Q2, they're traveling along their lanes, but there's a blockage in the lane which causes Q1 to have to go around and into the oncoming car Q2 in the other lane. And so this deep reach was used to compute both a reachable set in 10 dimensions, as well as a safety controller, which in this case, you can see both vehicles veer away from their desired paths, which are shown as the solid line there, to be able to resolve that conflict. Okay, and you can ask things like, well, you know, what happens with different initializations? So sort of query around the set and see the resulting safety controller based on that computed set. Okay, so that's kind of the introduction to reachability. And in recent years, we've been asking, can you use these reachable sets in a safe learning paradigm? In this style that Melanie talked about a few in the session right after lunch. So the idea here is, you know, this reachability tool assumes you have a model of the system up to some unknown behavior in those disturbances. So what happens if you don't actually know your model and you want to, or what happens if you have, you know, for example, the uncertainty in the disturbance is quite large. Can you use a pre-computed solution to this reachability problem, so that that value function from the Hamilton-Jacobi-Isaac solution, and scale up or scale down based on information that you're learning in real time about what the disturbance in the system actually is. So we call this an online model validation, and it's in fact, it's joint work with Melanie, where we initialize the kind of active unsafe set as the smallest candidate set from which you can guarantee safety. And then as the system is evolving and you're gathering information about the model, about the disturbances, you may see, for example, in this case, that you weren't being conservative enough, that you're at a particular point at state X at time T, where the disturbance is larger than you had predicted. So you can then show that by scaling to a super zero level set of that value function, you can guarantee, and under certain Lipschitz conditions of F with respect to the disturbance, you can guarantee safety. And over time, as you get more and more information about the disturbance, hopefully, you know, that set becomes smaller, that you gain more information so you can become less conservative about your control actions and move around in a larger part of the state space. Okay, and I think I'll skip this video, but it's kind of this a quad rotor, which was initially in its model, it had some understanding of its own dynamics with respect to wind in the environment. And then we immediately put a large fan disturbance into the lower part of that lab. And the quadrotor basically, you know, recognizes that that disturbance is much larger than it had computed a set for. So it kind of scales back its safe region to points where on the boundary of the safe region, it's doing this online model validation. It's saying, okay, the disturbances within the new set that I've computed comply with the reachable set that you know, I've scaled back to. Okay, so in the last 10 minutes of the talk, I'd like to go towards these, like this problem that I don't, you know, this is, one of the cases where I think we really want to use learning, which is not necessarily to learn about, about the dynamics or sort of disturbances in the dynamics of the system, but really things like unknown environments. You have a deep learning-based perception module, and that's kind of guiding you as you navigate through an unknown environment. And this is work that we presented in Coral in 2019, and I've given the archive link there. But it's sort of the experiment that we have in mind is a really kind of simple one. You have a robot with a camera, and it knows where it is, it knows its goal, but it doesn't know what's in between. It knows, I shouldn't be, it's been trained. We train a perception module based on environments like the one it's in, which is like indoor university labs. And then we ask it to control itself appropriately as it gets images in real time about its new environment. So we designed an architecture which is a modular architecture, perception module, which is where the learning scheme is, combined with a planning module and a control module, where the planning module and control module are very traditional. We use a spline-based planner and a linear quadratic regulator for the control. We assume we know a model of the system itself, so those are really kind of conventional planning and control model-based schemes. The perception module itself is trained, and it's trained using simulation data and optimal control. So we use an online database, which is called the Stanford Indoor 3D Spaces database. And that provides textured meshes of indoor lab environments of buildings on the Stanford campus. And we train it with the location and shape of the obstacles known, so that the cost for our optimal control problem is a sign distance function. We can set it up to, get to a desired target while keeping away from obstacles. And then we find a waypoint such that the resulting spline that we compute minimizes the cost. So in our architecture, the output of the learning-based scheme is a waypoint. It's a next waypoint that you want to go to, knowing where the final goal is. So a point along the path to your goal. And so that's what the learning module is. It takes in images, and based on known inertials and a known goal position, will compute the best next waypoint, or a best next waypoint from a set computed. We originally did this to kind of do a comparison with end-to-end learning schemes, which were learning all the way from images to the kind of action that you apply to the vehicle. And our hypothesis was that you don't need to learn all that. You can, if you have a good model of the robot that you're trying to control, you can really use, think about, scaling back where you use learning and use planning and control algorithms that, we've spent a long time developing in the control community. Okay, so we were able to show good results with this. This is just, this is from that Coral paper. And you can see the first person view. So this is what the robot sees. It's trying to get outside of a lab into a corridor. So it wasn't trained on doors. It didn't know about doors, but it was trained with a lot of data that indicated that to get, when you see this kind of configuration, look for a door so that you can, get out into the place where your goal is. And here, the nice thing to see is that glare on the floor. There's kind of, you're going from a carpeted room to a shiny floor corridor where it sees a lot of glare, and that doesn't upset it at all in terms. So we had a lot of these successes there. But we also had some failures, and this is one of them. Here, the robot is trying to get to a goal, which is around the chair, and it just kind of hits the chair. So this is one of the failure cases that we saw. And so we started to ask, how might we think about using reachability or using our control tools, maybe in a kind of redundant way, to avoid these kinds of failures. So could we design a, like a safe set boundary based on knowledge that we're gathering in real time from the camera on the robot? So we kind of developed a separate channel. So using that same camera, we used subsequent images in the camera. So to develop a depth-based sensor of where immediate obstacles are. And then we used that to kind of grow a safe space in the environment using a reachability-based calculation. And we did that in real time. So that reachable set then acts as a safety verifier that when we're applying the LQR controller to our robot, it first asks, is this going to run you into a chair or not? Or is this going to violate your safe space? And if not, it allows it to continue. If so, it applies that safe control to use on the boundary. Okay, so here's that same example, and what is a little bit different, you see in the upper right-hand corner, we're plotting that growing safe region of operation. So this backwards reachable set is actually the complement of the backwards reachable set from the obstacles. So this is work Samuel and Andrea Baichi worked on. So you can see there's where it would have hit the obstacle, and that's where it would have hit the boundary that would have led it to the obstacle, and it's being guided away by that safe control on the boundary until it goes back in and gets to the goal. Okay, so let's end by just talking about a few challenges. And I think these are, when I said open questions, I feel that these are kind of really exciting things to think about from the point of view of safe robot control as you're learning in real time, like big things, not Lipschitz continuous disturbances, which we were working on before, but you're learning about the environment, or you're learning about somebody moving around in the environment, or you have to interact with somebody and you're trying to learn about, what are their characteristics so you can interact properly with them. So these are some of the things that we've been thinking about, like for, anytime you have a learning-based component, how do you know that your learning-based component isn't going to fail? How do you make some guarantees about the behavior? And can you kind of have a control safeguard that monitors the behavior of that system? So one possibility is to have a monitor on the inputs to the learning-based component. Theoretically, you know something about the training distribution for that learning-based component. Maybe you can model that training distribution. So then as in real time, you can ask, are the images that I'm getting, are they in distribution or out of distribution? And if they're out of distribution, what do we do? Do we have some kind of safeguard? Questions about what does uncertainty mean in these learning-based components? So in our case, our learning-based component gave a waypoint as an output. So what is the uncertainty around that output? And how does that uncertainty affect the subsequent decision-making components in the loop? I'm showing you the easiest possible thing, right? It's a turtle bot with a camera inside a lab environment where there's nothing moving around. So, we're operating in real complex environments, and how do we deal with those more complex environments? So let me just summarize by saying we talked about safety from reachability analysis and how we might, kind of a method for adding new information into that reachability analysis, but kind of we opened it up to harder problems like unstructured environments. We talked about supervising learning using optimal control and one architecture that we have worked with. And then we're working on a couple of things now, a couple of directions. One is, this is with Andrea Baichi, how might you use, like if you have humans in your environment, for example, and then you're thinking about different ways that you might model the actions of those humans, how might you use reachability to analyze those predictive models of humans to come up with information like, okay, if this is the model, what do I have to learn to achieve high confidence in that model? We're working on, if I just click this left-hand side here. Yeah, so we're now making our environments more complex. This is Varun Tolani, who worked on that navigation in unknown environments. How might we develop new data sets to train that neural net to deal, that perception module, which is a neural network, to deal with more complex environments like people moving around. And then we've been working on integrating control, not just on the boundary of the set, but throughout, like you're moving with respect to these constraints. And that's something really beautiful that Melanie presented earlier. We've been working on the side of control barrier functions and have developed this idea. This is jointly with Kaushal Srinath's group at Berkeley on the idea of control barrier value functions and how we might use that for control. So with that, I'd like to conclude and just thank the students and postdocs who've worked on this, and many of the students who've moved on to positions in industry and academia and our funding agencies. And thank you very much for listening.
Thank you very much for a really great talk. We have some time for a few questions. Please raise your hand or post in the chat or directly speak if you're one of the speakers. So there's one question in the chat about deep reach.
Yeah, and the answer is not right now. So images are huge, right? We're working, so I showed you that 10-dimensional example. So we're working on, with Kaushal Srinath's group, on applying deep reach to the Cassie robot. So Cassie is a high-dimensional dynamic system, and we're looking at lower dimensional representations of Cassie in safe transitions from one gate to another walking gate using deep reach. But my feeling is that's, even with deep reach in terms of what we've done, so, okay, it's a new work and we've got more exploration to do, but I don't think these reachable set methods are going to scale well to the dimensions of images. I think they might work if we think about latent spaces of images, but then, we're missing a lot of information. So I think there's going to be some, thinking about the logic of using reachability in low dimensional representations, but then kind of going back to the high dimensions using querying or some of this work that's being done. Perhaps that Marco talked about, but yeah, I think the answer right now is no. It's getting us to higher dimensions, but not that high.
Claire, you mentioned an intermediate representation. Do you think that signed distance fields, you mentioned you use that to model the environment, right? So do you think that this is a suitable intermediate representation and kind of inferring that from images and basing the reachability computation based on signed distance functions?
It is for that problem we looked at. So Nikolai, you've worked on an architecture which has kind of a richer representation of the environment. Here, it's quite simple. We know where we are, we know where we want to be. So a waypoint is actually kind of a natural thing for us. We don't care about what else is around us so much as it's just something to avoid. So with respect to the task at hand, the idea of assigned distance function representation made sense. But I could see, as soon as we want to kind of recognize what's going on in the environment and react differently depending on what is going on, we need, I believe, a more complex representation.
Yeah, so sounds good. I think this is a very interesting discussion. We can, I suggest we move on to the last talk, and then we'll have a discussion where we can continue this these questions. So